Hey you guys, welcome back. Tonight we are actually starting with level M of the TABE Adult Basic Education Math. Level M is like the second level, the next highest up from the level E, which we just completed. This is the first lesson from level M, and it is about factors and multiples. So we're going to be talking about a couple different things in this lesson. We're going to be talking about greatest common factor, least common multiple, prime factorizations. I think there's one more thing I can't remember, but we'll get there when we get there. The notes that I am using, a blank version is posted on Google Classroom. If you would like to print one out, go ahead and do that. And if not, that's cool. You can make your own notes, or if you don't need to take notes at all, then, good for you. I mean, that's wonderful. So let's go ahead and dive right in. The first thing we're going to talk about here is the greatest common factor. So first of all, what is a factor, right? So in multiplication, a factor is just a number that when multiplied by another number gives a larger number. That's basically how multiplication works, right? And when you go backwards from that, like if you're doing division, then you're looking for two factors that when they multiply together, you get that larger number. So for example, in the first example here, we have 3 and 4 multiplied together make 12. 12 is that larger number. Therefore, we can say that 3 and 4 are factors of 12. Now, numbers can have many different factors. It's not just one or two numbers. And in fact, the larger the number gets, the more factors there are underneath it that will multiply to make that number. So we can represent this using factor trees. It's just how I always do it. I'll use 12, the one we just said, as an example. So 12, you can make that number 12 by multiplying 3 times 4. And you see how I did those little branches from the tree? So like 12 is like at the top of that tree, right? And then 3 and 4 are like the next level down. And when you multiply all the things in this level, you should get the next highest number, which would be 12. 3 times 4 makes 12. So are there any other ways that you can make 12? Are there two other numbers that multiply together to make 12? The answer is yes, there are. So first of all, any number has a factor of 1 and itself, because anything times 1 is itself. So 1 times 12 is 12. Therefore, 1 and the number are always factors of whatever the number is that you're looking at. Now, are there any other numbers that when you multiply, you get 12? Think about it. Think about it. Cool. Yes, there are. If you have 12, you can also represent 12 as being 6 times 2. 6 times 2 makes 12. And that's all there are. There's no more factors of 12, okay? But this is what a factor tree is basically. You just take a number and you try and break it down into its factors. Now, later in this topic, when we do prime factorization, you're going to see a tree that has many more levels to it, because what we're doing in that case is we're trying to break all the numbers down into the smallest possible factors that we can. But we'll get there in a little bit, so don't get ahead of yourself. Okay. Sometimes, actually very often in math, we need to look for common factors that two different numbers have in common. So if this is an example that's given here of the number 6 and the number 8. And what we're doing is we're looking at all the different things that multiply to give us 6, and a separate list, we're looking at all the different things that multiply to give us 8. And then we're looking at the two lists and we're trying to see what factors they have in common. So in the factors of 6 are 1 and 6, because 1 times 6 makes 6. And also 2 times 3 makes 6. So all the factors that I have for 6 are in order from least to greatest: 1, 2, 3, and 6. And you'll find that that's a very good strategy to follow for these types of problems, is finding all the factors, but then making them in a list from lowest to least to greatest, okay? Now let's look at the number 8. You can divide or multiply 8. You can get 8 by multiplying 1 and 8, because 8 times 1 will give us 8. Anything times 1 gives us itself, right? But what else inside of 8, what other numbers that are smaller than 8 can multiply to make 8? Well, you also have 2 and 4. 2 times 4 makes 8, okay? So that's it. That's all the factors that you have. The larger the numbers get, if you had, let's say, 50 and 60 and you were looking at factors of those, you're going to have a much longer list because there's way more things or combinations that multiply together in pairs to give us that large number of 50 or 60. So that's going to be a super long list. These are relatively small numbers, 6 and 8, so there's only a couple of factors to compare. Now, the thing is, you want to look at, because we're talking about common factors, we want to know what factors they have in common, right? So they have 1 in common because both lists contain a 1, and they also have 2 in common because both lists contain a 2. That's it. They don't have any other factors in common, okay? Now, another way to look at this too could be to say, like, let's say you have 2 different, like, cake recipes, for example. I'm just throwing something out there. Let's see if it sticks. If you have 2 different cake recipes, you might have like a recipe for like a bundt cake and then another cake, which is like a chocolate layer cake or something. The ingredients for those cakes might be a little different because the end result is something different. A bundt cake and a chocolate layer cake, they look very different. One has chocolate and frosting and stuff. A bundt cake is usually just like, vanilla or lemon or something. They're different in the end, right? The outcomes are different. Just like 6 and 8 are different numbers, right? Those are the cakes. But the things that go into that, they might have some things in common, and then they might have some things in the ingredients that are not common amongst the both cakes. So both cakes probably have flour in them. So that would be like a common factor. Both cakes probably have eggs in them. That's a common factor. Both cakes probably have vanilla extract. That's a common factor. But the chocolate cake is going to have cocoa powder or, chocolate syrup or something to give it that chocolate flavor. And the bundt cake might not necessarily have that. It might be a lemon bundt cake, and therefore it wouldn't have any chocolate in it. So those would be factors that are not common amongst the two things. But they are factors that make that lemon cake, or they are factors that make that chocolate cake. So I hope that gave you kind of a more concrete idea of how factors work and how common factors work. Now, the last piece of this greatest common factor thing is literally GCF, which is greatest common factor. That is, when you're looking at those comparisons of the factors, what factor is the biggest number that these two numbers have in common? So let's go down here and let's take a look. We have 12 and 16. Those are the two numbers we are comparing. 1 and 12 multiply to make 12. 2 and 6 make 12, and 3 times 4 makes 12. When we're looking at 16, 1 and 16, when you multiply them, make 16. 2 and 8 multiplied makes 16. And 4 times 4 gives me 16. Notice I didn't repeat that 4 in here because that would just be really confusing, okay? 4 times 4 gives me 16. I only have to list it once. It's fine, okay? Now, what I'm looking at here are my common factors, right? So that's just what we did in the last step. They have 1 in common. They have 2 in common. Both the lists have 4 in common, but they don't have 3 or 8 in common. They don't have 6 in common. They don't have 12 or 16 in common, okay? What I'm looking for is the largest of those common factors, and that is what the GCF is, the greatest common factor. You are going to hear GCF so many times from now on, it's going to make your head hurt. GCF is greatest common factor. Don't forget what it means. So the greatest common factor here would be 4, okay? And that, ladies and gentlemen, is all there is to it when it comes to finding greatest common factor. Okay, the next topic that's inside of this lesson is about something called the LCM, or the least common multiple. Okay, so this this is different than greatest common factor. What you're going to have is you're going to have those two smaller numbers, those factors, okay? And what you want to find is the least amount of times you have to find multiples of each of those numbers until you have something in common. That probably didn't make a whole lot of sense, but once you actually see it unfold in the numbers, it should click for you. Now, something I want to show you to kind of just make this, kind of concrete is a clip from a movie that I always think of when I think of least common multiple. So after I give you this example between 3 and 4, then I'll go ahead and play that clip so you can see what I'm talking about. But we are comparing multiples of two numbers. The numbers we are comparing here are 3 and 4. We're looking for the least common multiple. So what do we do? Well, we can take 3 and we can take 4. Make a big list here. And then if we multiply 3, we're gonna do this chart we're gonna fill the chart in for each number. So let's make a bunch of rows here so that we have a lot of space to fill in, right? The first thing we're gonna multiply by is 0, okay? And then we're gonna do 1 multiple, 2 multiples, 3 multiples, 4 multiples, and 5 multiples. And you could go on and on and on. Hopefully, with most examples that you work through, doing just a list like this up to 5 should give you all the multiples so that you can find the least common. But you might have to keep going and go to like 6 or 7 or whatever. So what we're looking at is what happens when you multiply 3 times 0. So that's 0, okay? And then 3 times 1 is 3, 3 times 2 is 6, 3 times 3 is 9, 3 times 4 is 12, 3 times 5 is 15. Okay, so we filled in all the 3's, right? Those are all the multiples of 3, okay? And you might think back to like the very first lesson we did, which was about skip counting. I am literally just skip counting by 3. So 0 plus 3 is 3, plus 3 again is 6, plus 3 again is 9, plus 3 again is 12, so on and so on. Let's do the same thing for 4. So we're going to do 4 times 0, which is 0. 4 times 1, which is 4. 4 times 2, which is 8. 4 times 3, which is 12. 4 times 4, which is 16. 4 times 5, which is 20. Okay, now there is something that you have to know, okay? 0 doesn't count. Cross out that 0 column because it does not count. 0 does not matter. It's not a least common multiple, sorry. Otherwise, the least common multiple of everything would just be 0. It's not 0, okay? So after you eliminate that 0 row, look at all the numbers that you have here, okay? What's the first number that you see that these two columns have in common if you go from top to bottom? The first number they have in common is 12, okay? Here's a 12 and here's a 12. It doesn't matter that you had to do 3 an extra time in order to get to that 12. These don't have to be on the same row with each other. All you need to know is what's the first combination of like 3 and 4 that gets you like a number in common or a result in common. You would say for the answer for this problem, the LCM or the least common multiple between 3 and 4 is 12, and that is all there is to it. So I think on my next, that's the only example I have for LCM because you're just going to do this same process, repeating it over and over again. There is a way to do it with prime factorization, but it's a little confusing. So the easiest thing to do is just do this multiples process, make the list, and see if you can find, the thing that they have in common. So I'm going to actually flip over and I'm going to let you see this clip from Father of the Bride. It's like one of my favorite movies from dating back to when I was a kid. Probably because it was one of my mom's favorite movies, so we watched it all the time. I don't know. But Father of the Bride, very funny. The sequel's very funny. If you've never seen it, give it a shot. I'm sure you can find it streaming somewhere. But anyway, I want you to watch this clip and I want you to like connect this least common multiple concept was something that happens in real life, and I can guarantee you has happened to you at the grocery store. So let's watch.
But mellowing out was not in the cards.
Excuse me, sir. What are you doing?
I'll tell you what I'm doing. I want to buy 8 hot dogs and 8 hot dog buns to go with them. But no one sells 8 hot dog buns. They only sell 12 hot dog buns. So I end up paying for 4 buns I don't need. So I am removing the superfluous buns.
I'm sorry, sir, but you're gonna have to pay for all 12 buns. They're not marked individually.
Yeah. You want to know why? Because some big shot over at the Wiener Company got together with some big shot over at the Bun Company and decided to rip off the American public. Because they think the American public is a bunch of trusting nitwits who'll pay for things they don't need rather than make a stink. Well, they're not ripping off this nitwit anymore because I'm not paying for one more thing I don't need. George Banks is saying no.
Who's George Banks?
Me!
That clip gets me every time. Man, he's so funny. All right, so the example in there was the hot dogs and the hot dog buns. This is least common multiple is how we can solve problems where we want to get the same quantity of something, but like the quantities are sold in different amounts, right? So like, let's say that you have hot dogs that come in packs of 8, I think. I don't know, 8. I don't know what they come in. Let's actually draw this example out. Let's do it. Let's see if we can solve the problem from Father and the Bride, right? So if hot dogs come in packs of 8 and the buns come in packs of 12, how many packages of each thing do you have to buy so that you don't end up wasting anything? So in other words, what's the least common multiple of 8 and 12? How many packages do you have to buy before you get the same amount of hot dogs and the same amount of buns? Okay, so this is a good problem to use this table for. I don't have any room here, so I'm gonna go ahead and I'm gonna erase this table. Right, we're just gonna make another one. Okay, we are erasing. Okay, so let's make our table. I'm gonna give myself some room here so I have enough space to draw all the numbers. Hopefully that's enough. So we have 8. That's the hot dog buns. They come in packs of 8, and then we have 12, which is the buns. I'm sorry, 8 is the hot dogs and 12 is the buns. So I'm going to skip 0 because we know 0 is never the answer. So 1, 2, 3, 4, 5, 6, 7. Hopefully it's not more than 7. I don't remember the answer. Let's do it. 8 times 1 is 8. That's 16, 24, 32. 40, 48, and 56. Hopefully I don't get any higher than that. 12, that's 12, 24, 36, 48. Boom, I think I found my answer, by the way. This is 60, this is 72, this is 84. Okay, so the first number, the lowest number that appears in both lists is 48. Okay, so you would have to buy 6 packs of hot dogs and 4 packs of buns in order for you to end up with 48 hot dogs and 48 hot dog buns. So that's the solution to that problem. Or, you could just do what he did in the movie, which was, be a crazy person at the grocery store and just like start taking the buns out of the package so that you could just buy like 8 hot dogs and 8 buns. You'd probably get in trouble for that. So Mr. Dansby did not tell you to do that. And that's it for least common multiple. Cool. So let's roll on here. We have 2 more things to talk about. One is called prime factorization. And in a prime factorization, we are taking a number and we are breaking it down to as the fewest the smallest parts that you could possibly break it down into. So I like to think of this sort of like Legos, right? So you know, Legos, a little plastic toy that you build, you notch them all together, and you make like a big. It's all little pieces, and then you make it into like a big figurine or something. You know, a building or a spaceship or whatever. So I like to think of this sort of like Legos. Let's say this is backwards. Like, let's say you have that spaceship Legos, and it's done already. It's built, right? If you take that spaceship and you break it in half, that's not broken down into its smallest pieces. You broke it down, but you haven't broken it down all the way. What you're trying to do in a prime factorization is take a number and keep finding factors and break those factors down even further as well. You might also sometimes find that you have a number that's prime, and a prime number, we will highlight this statement because this is something that people get confused about sometimes. A prime number is where the only factors of that number are 1 and itself. There's nothing else that goes into it. Okay, that is a prime number. There's a list of prime numbers you can find sometime if you're interested in looking that up. 1, 2, and 3 are all prime numbers. 4 is not, because 4 is not just 1 and 4, it's also 2 times 2. So 4 is the first number that's not prime. 1 is prime, 2 is prime, and 3 is prime. And then you can keep going from there and sort of like make some guesses. Let's look at our first example. Our first example is 5. If I wanted to break 5 down, I'm just going to guess here that I'm going to break this down into 1 and 5. Yeah, 1 and 5. It is prime. There's no other numbers that go into 5. Remember, factors have to be smaller than the number that you're looking at. So if you're looking at 5, think about going down from that. Does 4 go into 5? 4 times what gives you 5? Nothing. 3 times what gives you 5? Nothing. 2 times what gives you 5? Nothing. The only choices are 1 and 5, and therefore 5 is a prime number. Okay, now 16, right? So this is like a larger number, and some, you might struggle with like, where do I even start with a problem like this? What number should I try to divide it by first to try and start finding these factors? Well, if it's an even number, like 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, blah, 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 it's going in multiples of 2. If it's an even number, I would say start with 2. And a lot of times with even numbers, you can just keep breaking it down by 2, and you'll get it to its smallest factorization. So let's break down the first level here. I'll use a different color. We'll use blue. So if I divide 16 by 2, I get 2 and 8. Now, if I divide 2 by 2, I'm on the next level now. So like I'm done with 16, right? I'm at the next level of 2 and 8. Those are my factors. I want to keep breaking this down. Does 2 divide by anything else? Well, 2 divided by the only number smaller than 2 is 1. 2 is prime. So it's really just 2 and 1. So we can break this down as 2 and 1. But what about 8? Why don't we divide 8 by 2 and see what happens? If you divide 8 by 2, you get 2 and 4. Okay. Now 2, we already know, is prime, and this 2 is also prime. 2 is always prime. 1 is a prime number. 4 is not. Remember we talked about that a minute ago, right? Also, okay, so I just want to say that I made like a little bit, I goofed here. All right, listen, if a number is prime, I'm going to erase this and start over. If a number is prime, then you leave it as itself. You don't break it down as 2 and 1 when you're doing a factorization like this, because watch what would happen, right? If this was 2 and 1, I could keep breaking this down as 2 and 1 and 1, right? And then this would break down as 2 times 1 times 1 times 1. Like, it's gonna be like an infinite loop, and we don't want that. We don't want any of that. If a number is prime, then you just leave it as itself, okay? So since 2 is prime, we're just going to do a down arrow and put a 2. But 8 breaks apart into two numbers. Let's do 2 and 4, right? So 2 stays, this 2 stays, and 4. What does 4 break down into? If 4 was prime, we would stop here, but it's not. 4 is broken down into 2. Ooh, I should probably make that a tree. Sorry. 4 breaks down into 2 and 2. Okay, that's it. All you broke this down into was 2's, and all these 2's are prime, so you stop there. But the beauty of all of this, right, is that if you multiply 2 times 2 times 2 times 2, you will get 16. If you multiply 2 times 2 times 4, you will get 16. If you multiply 2 times 8, you will get 16. So if you're not getting the original number at every level that you go through here, you made a mistake somewhere, okay? So just be careful, all right? Let's go ahead and do 30. I'm going to actually ask you to pause the video and try 30 on your own. Try using this factor tree method here. Remember, if you hit a prime number, you know, just keep writing, keep bringing that number down, but you don't need to split it, okay? Pause the video, give this question a try, and then we will come back and do it together. Okay, so you should have paused the video. If you didn't, that's cool. It's not, you know, the easiest topic sometimes to understand. So 30 is an even number, so I like the fact that we could probably break 30 down by 2. So if I divide 30 by 2, that would be 2 times 15. Half of 30 is 15. And 2 we know is a prime number, so we're just going to bring 2 down. But 15 is not prime. 15 has factors in it, right? So 15 could be 15 and 1, or it could be, doesn't divide by 2, which means it's not going to divide by any other even numbers. But what about 3? It does divide by 3, and the factorization of that would be 3 and 5. Well, guess what? 3 and 5 are prime, because there's nothing that multiplies to 3 except for 1 and 3, and there's nothing that multiplies to 5 except for 1 and 5, and so that's it. If you multiply 2 times 3 times 5, you're going to get 30. And if you multiply 2 times 15, you're going to get 30. And those are the original numbers, so I know I did the factorization correctly. That's it with prime factorization. You're just breaking that big number, keep going down by factors until you get it to the smallest factors that you possibly can get. And prime numbers just carry through, okay? Okay, we have one more thing to talk about in this section, which is something called comparison equations. So a comparison equation is like if you have some kind of word problem or like a visualization of a problem that you're turning into a math problem, right? Because we do that all the time, right? We look at stuff, we look at random objects around us and we say, how can I make this a multiplication problem? Don't you do that? I'm joking, that's sarcasm. I don't do that either, and I'm a math teacher. Okay, so what we're doing here is we're finding the best possible equation that goes with our scenario that we have, okay? Because now that we have this beautiful thing called factors, there's many different ways that we can make up the same end result, but we're trying to choose the one that actually matches the situation that's being given to us. So let's look at an example. Soda from the store, if you buy like cans of soda, they come in packs of 12. Okay, I know they come in, you know, many sizes. We're talking about 12 packs right now, okay? So soda comes in packs of 12. So if I buy 2 packs, I'm getting 24 cans because 2 packs times 12 cans in each pack, 2 times 12 gives me 24 cans of soda. That's it. So the best representation of that would be 2 times 12 gives me 24, right? That's it. I could represent 24 a lot of different ways because ultimately I have 24 cans, right? I can take those 24 cans, those objects, and I can split them up many different ways. I could do 8 groups of 3 or 3 groups of 8, like 1, 2, 3, 4, 5, 6, 7, 8. That's one group. 1, 2, 3, 4, 5, 6, 7, 8 is a second group, and then 1, 2, 3, 4, 5, 6, 7, 8 is another group. Doesn't that add up to 24 cans? It absolutely does. Okay, and I can totally do that. It's mathematically, let's call it legal. You know, you can do that in math. But does that match the verbal situation, the word problem, the scenario that I was given? And the answer is no. Because I didn't buy 3 packs of 8 cans of soda. I bought 2 packs of 12. So this is out. I have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. That's my first pack. And then I have, is that 6? Yep. 1, 2, 3, 4, 5. I have 2 12 packs. And this accurately represents the scenario. Okay. Comparison equations are actually like a really good way for us to like make a stepping stone into solving algebraic equations. So algebra is we're taking numbers and we're adding those letters. We're adding those variables. Those variables could stand for anything. I'm putting my pencil down. Watch. So just tune into me for a second. When I say the word variable to you, okay? Variable means that literally it means that something is changeable. It can change. So when we're talking about algebra and we're talking about variables, we're talking about numbers that are not known to us. And we have to manipulate whatever we're given to try and like kind of solve for whatever those unknowns are. So let's think of like a real world situation, right? You know, let's say you're throwing a housewarming party. You just moved in somewhere and you're throwing a housewarming party. And you're going to the store and you're buying food, like, you know, chips and, you know, whatever you're going to cook for this party, right? So how much stuff that you're going to buy for that party is variable, right? Depending on how many guests there are, right? So like, you don't necessarily know how much food you're going to buy, and you don't necessarily know how many guests are coming to the party, right? That's actually 2 unknowns. That's really confusing, right? But you do know that, for example, if 10 people are coming, then you know that you need 2 bags of chips, okay? And if you double that to 20 people, well, you need to double your chips, okay? I'm just throwing out an example, right? So the thing that really is variable here, the thing that you really don't know, is how many guests are coming to the party. And algebra is all about finding those unknown values. Okay, it's not all about that, but that's like a big part of algebra, is finding those unknown values. So let's do an example. Soda bottles. So I'm not talking about cans anymore. I'm talking about bottled soda. Soda bottles come in packs of 6. If I bought 36 soda bottles, then how many packs of soda did I buy? So let's make a comparison equation that kind of models this situation. So I'll switch colors here. Let's do green. I haven't used green in a little bit. So every pack of soda it has 6 bottles in it, right? So I'm buying these in quantities of 6. What am I buying? I'm buying packs of soda. I don't know how many packs I bought in this situation, okay? Let's say that a pack of soda could be represented by a letter. We're going to call it P, okay? P stands for packs, all right? So 6 bottles times however many packs I buy should come out to 36, because they told me I bought 36 in total, right? How can I solve for the number of packs that I bought here? I can take 36 and try and figure out how many equal packs that is that makes 36. So 1, 2, 3, 4, 5, 6, that's 1 pack. 1, 2, 3, 4, 5, 6 again is another pack. Okay, that's another pack. How many bottles of soda am I up to here? This is 6. This is another 6, and this is another 6. This makes 18. I'm not there yet. 18 is not 36. So I know I at least bought 3 packs. I just don't know how many more than that. 1, 2, 3, 4, 5, 6. That's 6 bottles. 1, 2, 3, 4, 5, 6. Another 6 bottles. 1, 2, 3, 4, 5, 6. Another 6 bottles. That makes 18. What's 18 and 18 when you add them together? I just realized you can't see what I'm drawing. Sorry. What is 18 and 18 added together? 36. Okay. Moment of truth. Golden moment here. How many packs of bottles is this? 1, 2, 3, 4, 5, 6. There are 6 groupings. So the number of packs that I bought, the P, this letter P, this variable, this unknown amount, has to be 6. Because if they come in packs of 6, 6 times 6 makes 36 bottles. 6 times. That's 6 multiples of 6. Okay, I probably could have picked a better example that one didn't have 6 so many times, but whatever. You're going to see 100 algebra equations from this point forward, so here we go. All right, that is all I have. This was the next step up, and so I didn't want to kind of overwhelm you with too many things in this lesson tonight. There's going to be some delta math to work on that goes along with this. Remember, nothing that we really do in this course is like graded. Like, I'm not going to give you like an A, a B, a C, whatever. All the stuff I'm providing to you is material that you can use to improve your skills and eventually pass all those tests, okay? So when you log into Delta Math, yeah, it's gonna grade you because that's just the system that it's built upon, but I'm not doing anything with that grade. So I don't want you to do it and like feel bad if you didn't get 100% or whatever. The grade doesn't mean anything. What matters is that you are practicing. And the cool thing about Delta Math is that if I give you 5 problems of something to do, right, you eventually need to do 5 in order to earn that 100%, and that would be considered mastering that topic. So you can do 5 correct and do 5 wrong, and you did 10 problems altogether, but you got 5 right, and all I wanted was 5 right, and that's mastery, okay? So don't feel bad if you get questions wrong. Just learn from your mistakes and then correct them. Okay, guys, that is all I have for you tonight. Tune in next week for our next lesson, which will be Level M, Lesson 2, and Level M, Lesson 3. If you need any help whatsoever with anything that we've done in this lesson tonight or any other math topic, feel free to reach out to me, and don't forget to get your 3 hours per week of study time in Essential Ed. Thank you, guys. I will see you next time. Bye-bye.